The word matrix is derived from the Latin word mater, meaning pregnant mother or womb. A matrix in the mathematical sense is a rectangular or square, two-dimensional array of numbers, symbols, or expressions. Matrices have been around since the 1800s and were first used to solve systems of linear equations. These days, matrices and matrix operations have wide-ranging engineering and scientific applications. And of course, they have applications in the field of computer science. For example, matrices have applications in computer graphics, machine learning, cryptography, and quantum computing, to name but a few. In this video, I'm going to talk to you about some basic terminology and some fundamental matrix operations, including matrix addition, subtraction, and multiplication. I'm also going to suggest why these operations are so important, something you'll learn more about later. This is a matrix. A matrix with m rows and n columns is called an m by n matrix. M and n are known as the dimensions of the matrix. This matrix has 5 rows and 2 columns, so it's referred to as a 5 by 2 matrix. This matrix has 2 rows and 4 columns, making it a 2 by 4 matrix. This is a 3 by 3 matrix. It's also called a square matrix because m and n are the same. A vector can be thought of as a matrix. This row vector is a 1 by 4 matrix. And this column vector is a 3 by 1 matrix. A single value, that is, a scalar, can also be thought of as a matrix. This is a 1 by 1 matrix. All of these objects can also be referred to as tensors. A scalar value is a zero-order tensor. A vector is a single-order tensor. And a matrix is a tensor with an order of 2. A tensor can have any number of orders, but that is another story. So let's take a look at some simple operations that we can perform with matrices, starting with matrix addition. Well, this operation is rather simple. As long as the two matrices have the same number of rows and the same number of columns, you can add them together. It's just a matter of adding together corresponding values to generate a new matrix of the same size. Algebraically, the addition operation can be described like this. You may come across this type of notation if you read around the subject. Each matrix is denoted by a capital letter. Every value in each matrix is denoted by the same letter in lowercase, followed by its row number and then its column number. M is the total number of rows and n is the total number of columns. Of course, this kind of notation is really only useful if it helps you to understand the process. You can decide that for yourself. Matrix subtraction is just as trivial. As long as the two matrices are the same shape and size, we can subtract one from the other. In this example, a pair of 4 by 3 matrices result in a new 4 by 3 matrix. Algebraically, matrix subtraction can be described like this. When it comes to multiplying matrices together, the most important thing to remember is that the number of rows in one matrix must match the number of columns in the other. In fact, if this isn't the case, you will probably lose your way if you attempt to do the calculation. In this example, you can see that the first matrix has 3 rows and the second has 3 columns, so it is possible to multiply them together. The result, as you'll see in a moment, will be a 3 by 3 matrix. Notice that the symbol normally used to denote a multiplication operation is a dot. To multiply the matrices together, multiply each value in the first row of one matrix by its corresponding value in the first column of the other. Then sum up the products to get the first value of the new matrix. Here then, 2 times 3 plus 5 times 4 plus 4 times 2 plus 5 times 1 gives us the value 39. Next, multiply the values in the first row by corresponding values in the second column and sum up the products. Then multiply values in the first row by corresponding values in the third column and sum up the products. Next, we want the sum of the products of corresponding values from the second row of the first matrix and the first column of the second matrix. Then the second row of the first matrix and the second column of the second matrix. The second row of the first matrix and the third column of the second matrix. And then the third row of the first matrix and the first column of the second. The third row of the first matrix and the second column of the second matrix. And finally, the third row of the first matrix and the third column of the other. As you can see, calculating the product of a pair of matrices is a slightly more complicated process than addition or subtraction, but you'll get the hang of it with a little practice. I suggest you give yourself a few examples to do, with simple numbers like these, so you can focus on the method. Perhaps try a pair of larger matrices. You could even try multiplying a pair of square matrices together. You can check your own solutions online. There are plenty of free matrix calculators available that will let you do this easily. By the way, matrix multiplication can be described algebraically like this. Notice from the subscripts that the first matrix is being referred to as an m by n matrix and the second as an n by p matrix. This emphasises the rule that m in the first matrix must match n in the second. Is this a particularly useful description of matrix multiplication? Well, that's for you to decide. It will certainly make more sense when you've worked on a few examples by yourself. As I said before, a vector is a special type of matrix. It follows, therefore, that you can multiply a matrix by a vector. The result will be another vector. In this example, notice that the number of rows in the vector match the number of columns in the matrix, so the conditions for calculating a dot product are satisfied. To begin, multiply each value in the first row of the matrix with its corresponding value in the one and only column of the vector, then sum up the products. Now do the same with the next row of the matrix and the values in the vector, and then the next. In other videos, you'll see just how useful these operations can be. In animated computer graphics, for example, matrix-matrix multiplication is used to define elaborate combinations of transformations that can be applied to a 3D model. These transformations are applied to all of the vertices in a model in real time by means of matrix vector multiplication. In quantum computing, the quantum states of so-called qubits are represented with vectors, and operations that modify these quantum states are defined with matrices. Matrix vector multiplication is therefore fundamental to describing the operation of quantum logic gates. In machine learning applications, matrices and vectors are used to define the way the nodes in a neural network activate one another. Matrix vector operations are therefore fundamental to the training and decision-making processes of an artificial intelligence.